Hey folks, in this video we're going to take a look at one-to-one functions and inverse functions. We start off by looking at one-to-one functions. One-to-one functions, what you'll see, a lot of people will say a function is one-to-one if you pick a couple of numbers from the domain of the function that are not equal. So a does not equal b. That implies f of a does not equal f of b. So in other words, you take a couple of numbers in the domain, toss them into the function, f of a and f of b, and if these numbers in the domain aren't equal, you should get functional values that aren't equal. For example, the function x squared is not a one-to-one function, and here's why. I'm going to pick two numbers in the domain of x squared that are not equal. I'm going to pick 2 and -2. They are not equal to each other. So think of, I picked an a value of 2, I picked a b value of -2. Now when I evaluate the functions at these two values of x, well, f of 2, remember I put 2 in for x, 2 squared is 4. F of -2, put -2 in for x, -2 squared is also 4. I got the same value for y to come out. If this function is a one-to-one function, I would get different y values to come out. Since I got the same y value, the same functional value, it is not a one-to-one function. Another way to visualize this one-to-one function, and what this is really trying to say, is something called the horizontal line test. Think back to our vertical line test. Remember the vertical line test told us if we had a function. The horizontal line test is going to tell us if our function is a one-to-one function. And quite simply, here's how I'm going to verbalize the horizontal line test. If I can draw one horizontal line, just one horizontal line that intersects the graph in more than one point, it is not a one-to-one function. If every horizontal line I draw intersects the graph in only one point, then yeah, it is a one-to-one function. So what I look for when I see a graph, I look to see if there's one horizontal line I can draw that would intersect the graph in more than one point, and if that's the case, boom, it is not one-to-one. Now let's do a quick example. Let's say I'm just going to ask, which of the following are one-to-one functions? I'm just going to put up some graphs. So here's the first one. I don't know what the function is. I don't care. That's the graph of the function. The question is it a one-to-one function? Well, employ the power of the horizontal line test. No matter where I draw a horizontal line in here, it's only going to intersect the graph in one point. That means that yes, this is a one-to-one function. That's the graph of a one-to-one function. What about this one? There's the graph of a function. Question, is it a one-to-one function? The answer is no, it is not a one-to-one function, because I can draw a horizontal line right here that intersects the graph in more than one point. Heck, it intersects that graph in 3 points. It intersects that horizontal line intersects the graph in more than one point. It only takes one horizontal line to say that this is not a one-to-one function. So that's a quick overview of like a hardcore algebraic way of looking at one-to-one functions, but how this statement here is really It's really handled more nicely in the horizontal line test. So if you're asked, hey, is this function a one-to-one function? I mean, look at its graph. Fire up your calculator, make a quick graph, and let the graph tell you if it's a one-to-one function or not. Let the horizontal line test tell you. So next up, we're going to see why we need to know about one-to-one functions and the relationship to something called inverse functions. All right, folks, next up we're going to look at inverse functions. And I made a little comment up here. This is why we started off talking about one-to-one functions. Only one-to-one functions have inverse functions. I even put an exclamation point at the end of that. Only one-to-one functions have inverse functions. And, you know, can't really do much without coming back to my buddies, the old blob diagrams. So again, let's go through what a function will do. A function, remember, a function will pick up some element in the domain and it sends it over here to the range. So it picks up an x, the function drops it off over here at f of x. Keep in mind that this blob is representing the domain of the function f, and this blob, remember, is representing the range of the function. Okay, here's what an inverse function will do. Remember, only one-to-one functions have inverse functions. An inverse function will take this value, whatever it is, whatever that f of x value is, and it's going to send you right back to where you started. That's what the inverse function will do. The notation for inverse function is that. You read this as f inverse. Notice for the inverse function that this blob, well, it represents the domain of the inverse function. And this blob, it's the range of the inverse function. And I just want to point out a couple of things before we move on. A function and its inverse function. I'd like you to remember that a function and its inverse function, they're going to undo each other. It's kind of like, it's kind of like if if I stop by my bank this morning and I deposited $100 into my checking account, and then this afternoon my wife stopped by and withdrew $100. There would be, the net effect on my bank account would be nothing. I put in 100, she took out 100. They undid each other. That's what a function and an inverse function is all about. The function does something, the inverse function sends you right back to where you started. So they undo each other. The second thing I'd like to point out is this domain to range agreement. Well, what do I mean by that? And this is really important. Notice how the domain of the function, it must equal exactly the range of the inverse function. The range of the function must equal exactly the domain of the inverse function. I mean, that has to be true. So a function and its inverse function, they undo each other, and the domain of the function equals the range of its inverse function. The range of the function equals the domain of its inverse function. So, with all of that said, let me write up a quick definition over here. I'm going to block this off. This definition. This is the definition on how we're going to know if two functions, we just see two functions, how we are going to determine if they are inverses of each other. So let me just say, in general, two functions, and let me call them f and g. They are said to be inverses of each other. if when you do f composed with g of x, remember FOG, when you do that, you get x. And when you do g composed with f of x, you also get x. So two functions are inverses of each other. Then when you do the FOG of x, you get x. It simplifies down to x. And when you do GOF, it simplifies down to x. That's how you're going to know if two functions are inverses of each other. So before we go on and we do an example, let's kind of recap here real quickly. First, only one-to-one functions have inverse functions. How do you know if you have a one-to-one function? Well, if it passes the horizontal line test. Second, a function and its inverse function, I'd like you to think they undo each other. And you must have the domain to range agreement as exhibited in the blob diagram. In other words, the domain of the function must equal exactly the range of the inverse function. The range of the function must equal exactly the domain of the inverse function. And then finally, if you have two functions, f and g, how do you know if they are inverses of each other? Well, when you do this composition, it simplifies down to x. And when you do this composition, it simplifies down to x. Let's look at an example. All right, hey, here in this example, I'm giving you two functions. And I'm asking, show that the function f of x equals 2x plus 1 and g of x equals x minus 1 over 2. Show that those two functions are inverses of each other. So how do we determine if these two functions are inverses of each other? Well, we have to find the FOG of x and we have to find the GOF of x. And both of them have to simplify down to x. So let's do that. So first, do f composed with g of x, which you know to rewrite that as f of g of x. So that's f of, g of x, put g of x in here, x minus 1 over 2, that's g of x. So we're trying to find the f of x minus 1 over 2. Now remember, to find the f of x minus 1 over 2, it's this old process we've been through of evaluating functions. You're going to take x minus 1 over 2, and you're going to toss it in here for x. So you get 2 times x minus 1 over 2 plus 1. And now you simplify this. When you take 2 times this fraction, the 2's will cancel out. So you have x minus 1 plus 1. And x minus 1 plus 1, that simplifies down to x. So the f composed with g of x simplifies to x. We do not know at this time that they are inverses of each other because all we've done is the FOG of x. We also have to do the g composed with f of x, and it has to simplify to x. So we better do that next. Let's find the GOF of x. Again, you know to rewrite that as g of f of x. And see, f of x is 2x plus 1. So we're putting 2x plus 1 in for f of x. Now to evaluate function g at 2x plus 1, it's that old process of evaluating a function. You're going to put 2x plus 1 in here for x, just evaluating the function. So 2x plus 1 comes in here for x, and that gives us 2x plus 1 minus 1 over 2. And then clean this up. 1 minus 1 is 0, so you have 2x over 2, 2x over 2. That simplifies down to x. So f composed with g of x, it's simplified to x. G composed with f of x, it's simplified to x. At this point in time, we know function f and function g, we know they are inverse functions. Alright folks, thought we'd start, before we do this next example, I thought we'd look at something that I think is a pretty cool fact about a function and its inverse function. If you look at the graph of a function and its inverse function, on the same xy coordinate system, what you will see is that the graph of a function and its inverse function, they're symmetric about the line y equals x. So when you look at the graph of a function and its inverse function and the same coordinate system, you will see symmetry about the line y equals x, which is kind of cool. And we're going to use that fact to do this example. Notice in this example, I start off by saying, sketch f of x equals x squared plus 1 only on the interval x greater than or equal to 0. So only for positive values of x, well, and including 0. We're going to be able to use that graph to sketch a graph of f inverse. Well, hopefully, a little review time here, f of x equals x squared plus 1. Okay, remember, I expect you to know the graph of f of x equals x squared. I expect you to know what that looks like. So we know the graph of f of x equals x squared. It looks like this, plus 1. So that means I'm going to shift it up 1 unit. So here comes the graph of f of x equals x squared plus 1. It's shifted up 1 unit. And notice I don't care what's happening over here. I only care on the interval x greater than or equal to 0. So I'm shifting it up 1 unit. The graph looks something like that. That's the graph of x squared plus 1 when x is greater than or equal to 1. Before we do the graph of the inverse function, let's make some quick observations. For the function, the domain, x is greater than or equal to 0. So that's the domain. The range, well, let's look at the range. Looks like the smallest number in the range is 1, so it goes from 1 up to infinity. So 1 to infinity is the range. And before I do any work at all on sketching the graph of the inverse function, I know that the domain of the inverse function is 1 to infinity. The domain of the inverse function has to equal the range of the function. It's the blob diagram I started this off with. The range of the function is 0 to infinity. The range of the inverse function has to equal the domain of the function. It's the blob diagram I started off with. So, I'm going to sketch in one more thing. Going to sketch in the line y equals x. So here comes the line y equals x. I'm going to dash it. So this is the line y equals x. Okay, now remember my cool little fact here. The graph of a function and its inverse function are going to be symmetric about the line y equals x. So here's one little trick. Notice the point 0, 1 is on the graph of the function. Well, if I'm symmetric about the line y equals x, that means if I just swap those coordinates, I get a point that's on the graph of the inverse function, specifically 1, 0. Now, if I continue to imagine this graph being reflected around the line y equals x, that's what it means to be symmetric about the line y equals x, I should get a graph that looks something like that. That's not too bad for me. Symmetry around the line y equals x. This is the graph of the inverse function. And notice the domain is 1 to infinity, just like it should be, and the range is 0 to infinity, just like it should be. So when you have yourself a one-to-one function, like we did here, one-to-one function, to get the graph of its inverse function, you just have to go symmetry about the line y equals x. I showed you how to find a point. Hopefully this is making sense. Next up, is what if I give you a one-to-one function and I say, I don't want you to come up with the graph, I actually want you to come up with what the inverse function is. That's what we're going to attack next. Alright, hey, welcome back folks. We just looked at how we could use our knowledge of graphs of functions and being symmetric about the line y equals x to get the graph of its inverse function. Next up is how do we actually come up with the inverse function itself. To get the inverse function itself, it's actually a four-step process we're going to go through to get the inverse function. And what I'll do is I'll show you each step in working through this example. So here in this example, I have, let's find the inverse function for f of x equals 3x plus 2. I'm telling you f of x equals 3x plus 2. I'm telling you it's a one-to-one function and it has an inverse function. So here's what we do to find the inverse function. Like I said, it's a four-step process. I'm going to tell you what each step is. Here's step one. Step one. Replace your function notation with the variable y. So my function notation was f of x. I'm just going to replace it with the variable y. Notice that gives me y equals 3x plus 2. So step one seems pretty easy. Step two. Step two, you just switch the x's and y's. So in this equation, you just swap the x's and y's. Well, that means this becomes an x, that becomes a y. Step two seems pretty easy as well. Step three. Solve the equation for y. Okay, we're going to solve this equation for y. So here's our equation. We're going to solve it for y. We want to get y by itself. So we're going to subtract 2 from both sides. Then we're going to divide both sides by 3. Alright, we've solved the equation for y. That doesn't seem that difficult. There's only one more step left. Step 4. Step 4 is you're going to replace the y with the appropriate inverse function notation. Well, for this problem, that would be the appropriate inverse function notation. So we replace the y with the appropriate inverse function notation. Oops. And we get that the inverse function for f of x equals 3x plus 2. We get the inverse function is x minus 2 over 3. And some people are going to say there's a step 5. And step 5 is check your work. Do the composition to make sure you end up getting x. So if you do f composed with f inverse, it should simplify down to x. You do f inverse composed with f, it should simplify down to x. Other people say step 5 is to make sure you have that domain to range agreement that we've seen kind of pop up a couple of times here in this video. In other words, make sure the domain of your function is equal to the range of the inverse function. And make sure the range of your function is equal to the domain of your inverse function. But I'm just going to stop here at the 4 steps on how you actually go through the algebraic process of finding the inverse function. So you've seen how, if you have a function and its graph, you've seen how to graph the inverse function. Now you've seen how to find the inverse function. And that's it. I hope this is making sense. Thanks for watching.